Alright guys, I'm back again, another video lesson on electrolysis. This time we're going to focus on the electrolysis of water. In the last video I talked about how we can use electrolysis to create electrolytic cells that can break down molten sodium chloride or any ionic compound that you melt. But the problem with that is that you have to have such high temperatures for that to happen. It's not very practical to be doing the electrolysis of moltenized substances. So what we do here is let's take a look at what would happen if I were to try to do this in solution, because you know that a lot of ionic compounds dissolve in water and become aqueous when we put them into water, so they'll dissolve. So could I then, because remember the whole idea was that I needed those ions to be free to move around, right? They have to be in a solution, or they have to be melted down or in a gas phase so that these ions can conduct an electric current. Well, in an aqueous phase, they're going to conduct an electric current as well. So if we take a look at the two processes here, we've got the galvanic cell and electrolytic cell. I've got the same reaction going on. It's zinc and copper, but it's not really the exact same reaction, because notice over here it's zinc ions and copper solid. So I'm kind of reversing the reaction. So this would be the forward reaction. This you can think of as the reverse reaction. We know that this is a galvanic cell because of the positive voltage. So if the electrons are moving across, and you should hopefully be able to describe a galvanic cell. On the other side, we reverse the anode and the cathode for electrolysis. When we deal with electrolytic cells, the anode and the cathode reverse. Over here, the anode was the zinc. The zinc was my anode. The cathode was the copper. If you want to go back in the notes in the other video and look at that a little more closely, you can. Over here, the copper is the anode and the zinc is the cathode. They reverse signs. Why are they doing that? Because the electrons are moving the other direction. Here, the electrons are moving from the zinc, okay, and they're going over to the copper. That's the direction the electrons are moving in. Well, in this process over here, the electrons are actually moving from the copper to the zinc, because it's the reverse process. How is it happening? Because I've got this battery up here that's forcing the electrons to move in the other direction. Remember, electrons come out of the negative, go into the positive when we deal with batteries or any sort of power source that's included on here. Over here I add the voltmeter. I can measure my voltage. It's going to be 1.1 volt. Over here is going to need or require a minimum of 1.1 volt, hence why they have 1.5. It's way more volts than you need, so therefore we can get this process to happen. We can get this to go backwards and reverse the cell. Okay, so that would be the process. Now let's say we look at this process. Let's say we go back to our idea with the salt, and I put salt into water. Okay, so I've got aqueous sodium chloride. So sodium chloride aqueous is what I have in the beaker. Alright, so I got sodium ions and chloride ions in the solution, and then I put my electrodes into the wire with my power source. Electrons are coming out this way, so therefore this is going to be my cathode. Electrons are going in this direction, so they're coming off of this plate, hence why we have an anode. And it's important to recognize what's the anode and the cathode. Now, when we deal, what we want to have happen is we want the sodium ions to go to sodium metal. But when we deal with solutions that are aqueous, we have to realize that water is also in contact with that electroplate. So we look at the voltage. Now if I want to reduce, if I want to have reduction occur at the cathode, I look at which one I have. Okay, we will with all the substances that are coming in contact with that solution, or I should say with that electrode. Sorry about that. All right, so I've got reduction. Two reductions can possibly happen. Well, in order for water to reduce, in order for it to gain 2 electrons to produce hydrogen gas and hydroxide, we're going to need to add negative 83 volts. In order for the sodium to convert to the sodium metal, we would have to add 2.71 volts. So which one is more likely to happen? Is it likely that the sodium is going to turn into the sodium metal, or will the water turn into hydrogen gas? And as you can hopefully conclude, that the water will happen first before the sodium ion will change. And this is typical. Whenever you have any of those ions, whenever you have sodium ions, potassium ions, lithium ions, any of those aqueous soluble salts we talked about at the beginning of the year with double replacement reactions, the spectator ions, they are never ever going to form on this plate. You will always have water form before them. If you don't, you can go back and take a look at the standard reduction potentials. All of them are going to be more negative than the water. The general rule is that the higher the voltage, the more likely that reaction will happen at the cell. Okay, on that particular portion of the cell, on that electrode. I like to look at it as which one requires less energy. It makes sense that this one requires less energy, so therefore it's going to happen before the one that requires more energy. Now the same thing is going on the anode. On the anode, we've got water and chloride coming in contact with that metal, but if we look at the voltages for the oxidation, which one is more likely to happen? Well, if we look at this, these are pretty close, 1.36, 1.23 volts. We're going to go with and just say that the water is going to form and it's going to break down and form oxygen. So that what I'm going to see here is on these two electrodes, I'm going to see bubbles forming on both those electrodes. What I'm producing is hydrogen gas, not sodium metal. And over here I'm producing oxygen gas, not chloride gas. Well, I should say chlorine gas. A little side note, technically that would really be chlorine because notice the voltages are so close together that they kind of overlap a little bit almost. The reason why chloride will actually produce chlorine gas here is that the chlorine ion actually has a kinetically the activation energy is a little bit lower for that reaction, so therefore the chloride will actually convert. You're not going to do that in the AP test. Don't worry about that. You want to follow this rule here. Okay, the one that's the least negative is going to be the one that is going to happen first. Okay, again, I like to look at this, which one is going to oxidize first? Well, the one that requires less energy. Remember, the negatives tell us how much energy they need. All right, so enough of that. Let's move on. Hopefully you got some ideas there. All right, so what we look at is the overall reaction that's occurring at those electrodes is the anode, the water is breaking down. Again, the water is breaking down, producing oxygen and hydrogen. So the more, I already said that, I'm going to go back over that. So here's the two voltages. We put those two together. We add them up. We make the reactions even with each other. If I can't remember if the electrons were, I think we had to double this one. When we do that, electrons cancel. The hydrogen ion, and now notice I have hydrogen ion and hydroxide. Why would those cancel out? Because hopefully remember from acid and bases, when hydrogen and hydroxide come together, they make water. Since I have 4 hydrogens, 4 hydroxides, I would have 4 waters forming on the product side, and therefore waters will cancel out. And I'd have 2 waters still left over. So the overall reaction is the opposite process of hydrogen and oxygen coming together to make water. It's the water breaking down into oxygen and hydrogen. And notice that the water is actually going through both oxidation and reduction in this process. It's going through the oxidation here to produce oxygen. It's going through the reduction to produce hydrogen gas. Okay, so whenever you're dealing with salts and water, this is the moral here. This is what you got to get out of this. Whenever you're dealing with aqueous solutions, you have to watch for the electrolysis of water. How do you do that? You look up the voltages of both the water and the ions that are in the solution. Rule of thumb is those spectator ions, lithium, sodium, potassium, are never going to reduce there, so don't even look those up. If you see those 3 ions, they will stay in solution. The only way to get these to produce into solids is to have the solution melted down into a liquid that you saw in the other video. Alright, so that should wrap up the electrolysis of water. Alright, I'll see you later, guys.